Use Gaussian elimination to solve the system y minus 2z equals 0, 2x plus 3y equals 2, and x minus 2y plus z equals negative 1. I'm going to rewrite this below, but I'm actually going to interchange the first two equations, or the first two rows. And the reason I'm going to be doing that is because we want to get rid of the x terms in the second and third equation. We've already got an equation that doesn't have an x term in it, so we might as well move that down so that it helps us to move forward. So by replacing or interchanging the first two equations, I've got 2x plus 3y equals 2. And then I've got y minus 2z is equal to 0. And then the opposite of x minus 2y plus z equals negative 1. All right, remember that we want to get rid of 3 of the terms. And in this case, we've already got rid of one of them. So what we need to do next is to get rid of this negative x down here. Because we don't need to change anything in the first two rows at this step, I'm going to rewrite the first two rows just as they are. And then for the third row, to get rid of this negative x, what we can do is we can double this or multiply it by 2. That gives us negative 2x. And then we can add the first row, which will cancel out the x terms. So we're going to have 2 times equation 3 plus equation 1. When we do that, this gives us negative 2x plus 2x, which is 0. That goes away. And then here we've got negative 4y, because remember we're multiplying this by 2. Negative 4y plus 3y, which gives us negative y. And then we've got 2 times z, which is 2z, plus 0, which gives us 2z. And then on the right-hand side, we've got negative 1 times 2, which is negative 2, and negative 2 plus 2 gives us 0. So now we have 2 of the terms that we want gone eliminated already. Now we've got this third one that we want to eliminate. And the way that we can do this is by adding equations 2 and 3, because that will cause the y to cancel. So again, we're not doing anything to the first two equations, so we can leave those exactly like they are. And then for the third row, we are going to add equation 2 and equation 3. When we do that, nothing happens with the x's. We still have no x's. The y's cancel out. Y plus negative y is 0. The z's actually cancel out. Negative 2z plus 2z is 0. And we need to put something on the left-hand side. So because everything's canceled, we're just going to write 0. And then on the right, when we add equation 2 and 3, for the constant terms, 0 plus 0 is 0. And so in this case, our variables disappear, just like the last system of equations that we solved. But in this case, we end up having a true equation rather than a false equation. So we do not have no solution. This is going to be an entirely different situation. When we're solving a system of 3 equations with 3 variables, and using row operations, we end up with an equation that's always true. What that tells us is that there's going to be infinitely many solutions. But we can actually do better than this as far as a final answer is concerned, because they're not just random solutions. We actually have a system of 2 equations with 3 variables that we can use to figure out what those solutions are going to look like, where they're going to be in 3 dimensions as far as the x, y, and z coordinates go. So what we're going to do is we're going to solve this second equation for y in terms of z, and then that'll allow us to solve for x in terms of z, and then we can create a parameter that will tell us what all of the solutions are. So if we take this second equation, y minus 2z equals 0, and we solve for y, we do that by adding 2z on both sides, and that tells us that y equals 2z. So whatever z is, we know that y has to be twice that much. Now we can plug this into the first equation to figure out what x is going to be in terms of z. We've got 2x plus 3y equals 2. We know that y is equal to 2z though, so we've got 2x plus 3 times 2z equals 2. 3 times 2z is 6z. Now to get the x term alone, we can subtract 6z from both sides, giving us 2x equals 2 minus 6z. And to get x alone, we divide each of the terms on both sides by 2, giving us x equals 1 minus 3z. So we could say that x equals 1 minus 3z, y equals 2z, and z equals z. This is one way to do it, but it's better, instead of writing all of these in terms of z, to write them in terms of a parameter t. So if we let z be any real number t, that tells us that z is equal to t, y is equal to 2 times t, and x is equal to 1 minus 3 times t. So this gives us a way to write what our solutions will look like in terms of a parameter t. And you will see later in Calc 3, if you end up taking Calc 3, that this is a way that we can parameterize a line in 3 dimensions, where we've got x and y as the 2 axes in a plane, and then z is actually perpendicular to both of those. So we can use x and y to parameterize a plane, which is 2 dimensions, and we've got x, y, and z, which gives us 3 dimensions, and this parameterization would actually correspond to a line in 3-dimensional space, and all of the points on that line would be the solutions to this system of equations.